Drake's Lounge Australia, the February edition, 2023. Some announcements real quick. We did put out the February SARA Journal. So if you're a member of SARA, you got a link for it. The Western Conference is, you can sign up for that on the SARA, you go to the SARA store, look up Western Conference, and you can sign up for the online version of that. We'll be headed there, and it'll be in Bishop, California, at the Owens Valley Radio Observatory. So we'll have a little problem with doing a live feed at the antennas because you can't bring electronics to the antennas. But we're going to be in their conference area for the meeting, and so we'll get some of that stuff. Let's see. We are waiting in the fall, the ARRL antenna book, which has our input. It will be out. Just talked to the principal editor, Ward Silver, and he loved the stuff we did, and they are actually turning it over to the headquarters, and they will, they expect it in the fall. Ted Klein's online. Ted is the software guru about the easy radio astronomy, which we'd like to work with you guys on getting some of your Southern Hemisphere hydrogen data and vice versa. A lot of us are using the Scope in the Box software and Ted's EasyRA software, and you can just give a quick thing about the YouTube videos he's put up just recently. We're trying to get a group together to put a very large antenna array proposal together. That's just so that we could start working with the very large arrays and the ALMA and the European arrays, et cetera. And so we would like to sort of get a proposal built just for a learning curve. The Eastern Conference is now scheduled to be at Green Bank. That'll also be a hybrid online course or online. It's going to be in August. And let's see. That's all I've got for now. And I'm going to turn it over to Paul. He knows most of the people who are giving presentations today. Go ahead, Paul.
That's better. Thank you, Rich. Western Conference, I looked at the time difference and it's really awkward. I'm not quite sure whether any of us will get to that live. I think the Eastern Conference is an easier one. There are better overlaps with time zones, but I think we're 14 hours ahead or something. No, even more than that for the Western zone. So I don't know whether anybody will be able to get to that from this end, but I'll certainly keep an eye open for it. And there'll be recordings presumably, so we can catch up later. Good morning to all Australians and good evening to our US friends. And the big news from this end, I think, is Phil and the visit to Parkes Radio Telescope. So a group went up very recently and spent some time at Parkes. And Phil, if you're able to give us a quick rundown on what happened, and then there may be some questions about it. I think we've lost Phil at the moment. We're not getting any sound, Phil. Phil's up at our dark sky site and the internet access comes and goes a little bit, I think.
Phil hasn't said anything wrong so far. He's doing
no.
well.
He's very shy and retiring. No, he's still not there. No, we might have a bit of a fiddle around with your settings, Phil. Can you hear us? Yeah. Steve, have you got anything in your head about Parkes?
Well, it was a wonderful experience. Yes. I'll see if I can bring up some photographs. I'd never been there for a guided tour. I'd seen the place from a remote distance, but this was the first time I'd ever been at the property.
Now, for those that don't know, the movie The Dish was based on Parkes radio telescope.
Everybody seeing that?
Yep.
It's a photograph. Okay, so that's as we approached from the car park. And let me see if I can quickly scroll through these images. There we go. That's me out the front. Family snaps. I'll try to be brief on some of these. It's a magnificent telescope, 64-meter diameter. And we were given that's a earlier receiver setup that's on display out there in the paddock. We were given a guided tour of the property. And this is where John Sarkisian, the primary interface we had to deal with. He is a public outreach scientist, also works at the observatory. And he was pointing out that Parkes was used to look at the telemetry and obviously relay the Apollo 11 mission. And he was pointing out Neil Armstrong's heartbeat, which was on the telemetry just as he put his foot on the surface of the moon in 1969. And it was 112 beats a minute, whereas Aldrin inside the landing module, who hadn't stepped out yet, 81 beats per minute. But even 112 beats per minute looks like pretty cool character.
Pretty cool. Oh, yeah.
Yeah. So I'll quickly move on. This is part of the laboratory area of the observatory with lots of Hewlett-Packard test equipment in sight, some earlier receivers that they decommissioned. That's John Sarkisian, who was our guide. That's the original control panel for the control of the dish. And then we went up inside the property, and this is the astronomer's kitchen that featured in the movie, as Paul mentioned. And there's John Sarkisian sitting at the control panel, bringing up some various spectral screens that are shown. This one's the hydrogen spectrum. And it was curious that there was this other very, very large signal at 1380, which he wasn't prepared to tell us too much about. What else we got here? So yes, these things are all live. Current receivers sitting up there and showing that they've got activity on them. The telescope pretty much runs 24/7, and it's got months in advance of booked schedules. And while we were there, it was always whizzing around at different objects and various programs from different universities and organizations all over the world who remotely access it and slot in their schedule. Some of this equipment is old. It's really on display. It's not being used. And I noted things like this bank of square law detectors. The guys tell me that that's no longer in use, although it is on show. Various noise sources as well for reference noise signals. Some beautiful racks of equipment. I don't know, this sort of stuff makes my mouth water. I'm not sure about you guys, but it's delightful stuff. Again, racks and racks of Agilent signal generators. I think they're on use for reference sources. Beautiful stuff. Another one of me. Optical fiber, the communication link between the feed point down to the receivers in another part of the property, done by optical fiber. And that's the current control panel. And they reckon it's a little bit retro, like that other one you saw that's been decommissioned. But this is the live control panel up on the dish. And they liked it in that retro format because they're quite familiar with it. These racks of equipment were for the SETI program. And there was 2 cabinets there for SETI. The whole structure of the dish floats. There's nothing mechanically connecting the dish to the base. And it's sitting there under the force of gravity. And as it rotates in azimuth, they're constantly cleaning the friction surface there. Something that they do on a regular basis is, this is a little bit of video of it actually moving. That's right, but quite slowly. And John, our guide, seemed to be happy for us to walk around underneath this thing while it's moving above our heads. there's other antennas in the field at parks, and we saw that from the elevated position of being up on the dish itself. And recently, Phil will tell you a little bit more about a meeting we had just last week with the parks people, and they were suggesting that we could do collaborative work in conjunction with possibly one of these dishes that's in parks. What did I take this photograph for? Oh yes, looking up in at the structure while the cockatoos are looking down at us. I'll leave it there. Is Phil been able to join in with sound?
Can you hear me?
Yes.
Yeah, you can. So I tried to start a PowerPoint and that took the set audio away from me. So I don't know what's going on there. I won't bother. Yeah, that was excellent, Steve. Good talk. It was interesting.
Phil, before you go on, can you just give our US friends an idea of where Parks is, because they may not know?
So if you know where Sydney is on the map of Australia, which is on the east coast, Parks is about, was it 200 or 300 kilometres? It's trying to think in miles. It's 100 miles then, something like that, west of Sydney. So it's into the inland, pretty much inland of New South Wales, the state of New South Wales. So for us, it was an 8-hour trip. We met here at our astronomical site here, and jumped on a bus and travelled for a good 8 hours. And boy, that was a long 8 hours, I tell you. Once we got to this township of Parks, we stayed the night, and then in the morning met up with John Sarkisian and the guys at CSIRO in the Parks Observatory there. We spent the first 2 hours having a discussion with John and his engineer. There was a chap by the name of Franco. And we talked to them about what we can do to improve our radio dish and what steps we can take to make it better. And they were amicable to talk with us for the 2 hours and answer all of our questions. There was a group of others with us who were just normal optical astronomers. So there was a bunch of the radio astronomy guys, and then we invited other people from the club who were not radio savvy, but still astronomers, and they asked questions that appeased them, and they were happy to, like the CSIRO guys were happy to answer all the questions. And then at lunchtime, they came and sat with us at lunch as well, and the discussions went on. It was wonderful. And when we did the tour of the actual dish, we broke into 2 groups. So whilst one group was looking through all the engineering workstations and the workshops and going into the dish itself, one of the other guys sat with the other group and we talked more. So they were very forward in coming and talking to us and helping us out with our questions. And the whole trip was a hit. It was fantastic to do. When we got back, about 2 or 3 weeks later, John Sarkisian from Parks gave me a phone call, and he said that he had been speaking to other colleagues of his and that they wanted to get in touch with us so that we could actually help them out, and they'll help us out with some of our technical issues. Because being professional astronomers, apparently time is their biggest difficulty, whereas as amateurs, we have all the time in the world, and we can, if we like, decide to look at one object in the sky for 6 months. They don't get that. So they're keen for us to do some of the experiments or observations that they can't do, and then pass them the raw data, and they're willing to then analyze that data. So things are going forward in that part of the world, and it's just exciting for all of us here. I'm sure
that meeting had that meeting, Phil, didn't it? Had several of their scientists and engineers involved in that Zoom session with us as well.
Yeah, we had a meeting on Thursday, just on Thursday night, this Thursday, with members of the CSIRO. There's engineers, scientists, all that sort of thing, and yeah, they were like, "What? These are the things you can do for us," and they gave us a whole list of different types of observations that we can do, and they were, forward in trying to involve us with their efforts. So yeah, that was
some of the programs. They sort of gave a very broad scope of some of the programs they thought we might be interested in working on, but I think it's in reality they're a little bit out of our league. One of them was to look at water masars in Orion at 22 gigahertz. But our dish only goes to 10, so that was a little bit ambitious. Methanol was another thing that they were interested in. That's 6.7 gigahertz. Now that's within our scope. But another one that's a little bit closer was the hydroxyl at 1.665 gigahertz, 1600 megahertz. That's just a little bit above hydrogen line. And there's some very interesting work that's incomplete studies from their point of view. And they thought we could even get involved in doing some of that. To be honest, I think, Phil, isn't that really a little bit long term for us just yet?
At the moment, yes. I said this right at the start when I got the request to collaborate with them. We'll have to bite off more than we can chew, and chew real hard to achieve what they're asking us to do. But I think, if we bite the bullet and go forward, I think we can achieve something at least. And in the process, we'll be learning, and that's the goal, to learn.
Well, one of the things that's a southern sky object for us is the Velar pulsar, and that's been detected to have a glitch in its cycle, and that's very excited the parks people because they haven't had the opportunity to study that. Apparently a New South Wales radio amateur with his own amateur radio telescope detected it. Tim Bateman, he caught a capture of the glitch. His equipment, however, didn't have all the time stamping and all the sort of scientific inputs that would have made it more useful to everybody. So that's a lesson for us all. But I can't imagine how many times John Sarkisian stressed the benefits of us studying the Velar pulsar. And they're very keen for us to get access to the software that does the spectrum folding. They're very keen for us to just point our telescope at Velar, see what we can deliver, and then maybe plan a long-term study of that particular object. So that's completely exciting, completely new for us too, isn't it, Phil? We've never actually tried to detect the pulsar yet.
I think we might have pointed our dish at the Crab Nebula once, and that was it. There was nothing there.
Go ahead,
Steve Olney, who's down there with you guys, I forget exactly where he's at, has been.
He's in New South Wales too.
Yeah, he has a real-time monitor on that. Also, the DSES 18-meter radio telescope here in Colorado, which I'm a member of, has we've picked up Vela. It's just high enough, 2 or 3 degrees above the horizon at certain times to pick it up. So we've picked it up a couple times. I'm not sure we can maintain a long-term thing to catch a glitch, but so if you guys need any help on getting the pulsar data or pulsar software going, that I'm actually pretty good at that. And of course, Wolfgang is the master of that. So we'll get him online too to help you guys.
I've got a comment, a quick comment. Veer was a really good target, and you know, I know the folks down here in Tasmania have done a lot of work on that. In fact, I did my PhD on the Vela pulsar glitches. The thing that would be really useful is measurements around the time of the glitch at wavelengths that other folks aren't looking at, to have a look at how the magnetosphere is disturbed by the glitch. So that'd be really good. And then once you've mastered Vela, there are a couple of other fairly bright pulsars that are known to glitch in the southern sky that would be worth keeping tabs on. I had a look at a couple during my PhD, didn't see a glitch, but you know, these things, the more we observe them, the better we'll understand them.
When you say different wavelength, Andrew, are you talking about somewhere quite far away from neutral hydrogen spectrum?
No, I would say, look, I'm just thinking that the folks down here were looking at around about 1.2 gigs. I was looking at 950 and 650. So anywhere between about probably 500 megs and a few gigahertz would be really good. So yeah, coordinate with the Parks folks to see what they're doing. I can find out what's happening down here in Tasmania. They've got a 15-meter dish which is looking at Vela fairly continuously, and pick some wavelengths that other folks aren't looking at.
Well, to be honest again, Andrew, that's still a little bit long term for us. We've got one receiver and it'll do neutral hydrogen at the moment with a 6 megahertz 3 dB bandwidth.
I think the key on pulsars and neutral hydrogen is the pulsars are actually the brightest around 400 megahertz, and but you get higher wavelength at the higher frequencies. Higher not wavelength, higher bandwidth, and you get less interference there. So we've been doing 400 megahertz, but because of all the traffic around here, we've shifted up to 1380 to the problem is you don't want to do 1420. You want to be off the hydrogen because that'll jam you. So you want to get as low as you can or as high as you can above the 1420 line, so that you're and then you get, if you get 2 megahertz bandwidth, or the highest bandwidth you can get is the key after that.
Yep.
So
yeah, because one of the problems is the lower you go, you get more dispersion. So you've got to kind of deal with that in software. But the other thing that the Parks folks could really help you with when talking about multi-wavelength is different feeds that give you, multi-wavelength and possibly off-axis viewing as well. So you could maybe even observe, multiple objects at the one time with one dish. So that would be a really interesting thing to work for.
I agree. Long term again for us, to be honest, long term. I could explain a little bit more about that if you're interested. I could bring up issues related to our current refurbishment, Phil. I don't know if you think about that.
That's where I was heading just now. That's where I was just heading right now, Steve.
Yeah, you might want to get into the temperature dependence, because Ted was talking about that before you logged on, and dealing with temperature variations in software. So I think is that one of the main issues, Steve or Phil?
So after visiting the guys up at Parks, yes, we came back from Parks thinking we do need to do some more work on our receiver and on our software. And as a thing from that is that we've pulled our receiver off our antenna. We've taken it, Steve's taken it, and he's working on it now. And another thing has happened in the meantime since the last time we saw you chaps. Our dish, which runs on a lead screw to tilt it up and lower it, has developed a clunk, and we've taken the gearbox off to have a closer look at the reason why it's doing that. We think we've got a reason, and it's not damaged in any way. So it's just a matter of time now of getting everything back into place. So at the moment we're dead in the water, but hopefully doing the right things to make our receiver better and our mechanical lifting and lowering better.
Have we got the video?
Steve can probably tell you.
Have we got the video?
Show that.
Yeah.
We could
That
show
was-
that if
Steve's
you're
got
really
it.
interested.
It's worth
Well, I'll see if
watching.
I could. Well, it's not as bad as you think, though, Paul. After we had a good study of that, it's actually fairly quiet the way it does actually shift through that transition point. And
Sounded
the
pretty
reason
drastic.
why is that, well, the reason why, Paul, is that Mitch pumped in 2 tubes of grease into the joint. So I think that was one of the main reasons why it was having a problem. It wasn't lubricated properly.
No.
Where are we now? Servicing. There it is. I found the video. So this is you got to turn your volumes up. Hear it. So get ready for this. I'll just set everything up here for you. All right, take that off. Come on, get off the big screen. Now go to share. And I've got to share sound. So now you're seeing a video on the screen.
Yeah.
Stationary. All right, I'll just play that clip. It's repeated a few times. So what you're seeing is this is the jack screw. So it's coming down. It's coming down in altitude and pointing. Well, sorry, it's actually going up, isn't it? It's pointing to zenith as the tilt plate here is coming down. And we're seeing this jack screw going from left to right, which in our case is north to south, as it goes through this balance point in the transition. I'll just wind it back a bit. Now that's quite subtle, really. We get off that screen. There we go. Stop sharing. So that's quite subtle compared to when it was a dry joint. It was banging around and the lead screw was flapping in the wind. Very scary. So we had no choice but to sort of pull it down. And these things are several hundred kilograms. That angle plate that the jack screw goes through, that had to be brought down with it. Quite a monumental task amongst amateurs. And we think we can put it back together, don't we, Phil? It doesn't look like it's going to be quite a serious thing to deal with at all.
We're hoping not.
Just needed the inspection, good cleanup, and we need to maintain our structure a little bit more often. It has been neglected through the 2 years of pandemic, and then we've excitedly gone up there from time to time and used it. We've used it remotely, but we're not monitoring maintenance when we're using it remotely.
Is the hinge bearing clean and lubricated, that the point of rotation isn't sticking?
Yeah,
No,
we checked that. It spins really easily. Yeah, it was a contentious thing. We were thinking, oh, is it that? We had that exact thought in our mind, and as soon as it came off and we wiggled it, it just spun. There's no problems with the bearings.
So you've got a sort of a balance point, haven't you? When the dish gets to about 60 degrees, was it, Phil? 55 or something? It suddenly wants to tip over.
The theory is 45. Yeah.
45? Yeah, it suddenly wants to tip over and come down, which is good. It wants to point vertically. But the concern that we were told by the chap who fabricated the mechanism for that jack screw was that if that's stripped out and we don't have any safety mechanism, no chains, no movement prevention, if that was to slip out when it was tilted the other way, the dish would swing over and bang against the tower. So that could cause serious damage. All right. That's one problem we're trying to deal with. The other problem is the receiver. Do you want me to go on, Paul?
Well, I'm interested in the temperature dependence because Ted's got something to offer there with the graph that he just put up. Do you want to just touch on the temperature issue?
Well, it's a bit more complicated than that because I don't think the SARA group are fully aware of our current receiver configuration. I'll try to whiz through that quickly. Shown on the screen is our configuration. So the dish with a low noise amplifier and a, oops, that's not what I wanted to show. Oh, this is it. There we are. So that's the, I've written this specification back in 2021, which is a combination of my information plus details about the receiver that we purchased from radio astronomy supplies in the United States. So the radio astronomy supplies receiver is in 2 parts. It's got a front end, which is in a 19-inch rack box. that contains the front end. The external to that is a low noise amplifier that's on the feed horn. And then there's the back end, which is in our radio laboratory, the air-conditioned environment. That's another 19-inch rack unit, and that's shown there. We've got a RF splitter because one part of it we send off to software-defined radios or spectrum analyzers, and then the actual back-end circuitry is there. So this is the configuration of our receiver. There's 2 low noise amplifiers in series, one close to the antenna feed horn, the other one inside the receiver box. It's got a triple conversion in spectral mode, but in continuum mode, it's a double conversion. The first IF 400 megahertz, second IF at 70. So that 70 megahertz was originally coupled to an optical fiber link, which blew up on us and we had to remove it. So in the interim, we went over to a coaxial link, and that's still our current thinking, to remain with the coaxial link between the tower, the dish, and our radio laboratory. So back at the receiver back end, there's that splitter I talked about. That's a very convenient function for us. It doesn't affect the receiver sensitivity significantly. And in the design, this is not our design. This is the Radio Astronomy Supplies design. When you switch between the continuum mode and the spectral mode, in spectral mode, you bring in another IF, 21.4 megahertz IF, with a narrow 7.5 kilohertz bandwidth. And that's to sweep across the full spectrum, the 6 megahertz spectrum, to do Doppler shift studies over that spectrum. When it switches into continuum mode, which is the complete composite energy in the 6 megahertz bandwidth, they switch in this 15 dB attenuator to try and make these 2 output levels comparable. I'm not so happy with that attenuator. I never like big attenuators in a receiver path. The other part of the back end is this square law detector, and then a series of DC processing circuits, fixed gain circuits, adjustable gain circuits, adjustable integration time circuits, DC offset circuits. And the end result is a voltage, which is then converted digital to analog to digital. And that's what we process on our computer. Some of the circuitry there, that's a reverse engineering by me, but also diagrams that were eventually published to us from Carl Lister, the designer. Some people may know this man, some people may know of his work. There's the square law configuration for the square law detector. And I'll stop there because that's one of the most significant problems in our receiver, was the drift on that square law detector. However, that is inside an air-conditioned environment in the laboratory. The other problem we have is what's happening up on the tower. And the receiver up on the tower, I'll show you this documentation now. So I did some modifications to this receiver a year or so ago, 1.5 years ago, to install a status monitor, which was a microcontroller-based temperature humidity sensor. And it also monitored the flow of air with a fan inside the receiver front end. So what we're seeing here is the inside of the front end. That's the front end of the receiver after the first low noise amplifier. It's got a power supply board and a Peltier cell control circuit. This is the fan that we monitor the speed of, and that's to circulate the air inside this chamber. And the Peltier cell is sitting on the lid. You don't see the Peltier cell in this photograph. It sits on the lid when you put the lid that seals up the air volume inside the receiver box. And that's that 19-inch rack enclosure. And the temperature humidity sensor was sitting there. So after running this thing now for a year or so, we've started to get some pretty good statistics on its performance. And this is that output of the status monitor, where we have in the red line here, this is the power supply feeding that receiver. You're seeing the voltage fluctuate a little bit, and the current is the red line. The current in idle is the typical idle current of the receiver, 0.39 amps, but it jumps up to about 4.8 amps when the Peltier cell kicks in. But you see during this particular day, from about 9 a.m. all the way through to 10 p.m., the Peltier cell was on continuously, not switching on and off at all. And during that period, the internal temperature of that receiver was cooking up to about 32 degrees centigrade, shown by that red line, and that's the temperature scale there. So that was a fairly warm day. When the Peltier cell does go into its cycling mode here, where it's on and off during the cold evening, you do see the internal temperature of the receiver flat line, and that was at about 22.5 degrees. So we got some stability. The thermostat on the Peltier cell was set to 23. So the other thing to look at was a day where it was fairly cool. So that was a hot day. This was a cool day, and it only got warm at about this is about 3 p.m. through to about 8 p.m. And there the Peltier cell was cycling. So the Peltier cell was working, but it was managed to maintain the temperature, and you can see that temperature stabilized at about 23. But the other thing is, during the other part of the day where it was cool, the Peltier cell turns off and remains off, but the temperature inside the receiver is dropping. So on a cool day, the temperature drops. So what have we got here? We're trying to stabilize the temperature of the receiver, but on a cool day, it drops down to as low as, in this case, about 8 degrees. On a warm day, it can go up as high as 32 degrees. So fundamentally, the Peltier cell is not stabilizing the temperature of the receiver at all. So that's a fundamental that we've got to sort out. And I've made proposals now for quite a number of changes to be done to this receiver configuration. Originally, we had the low noise amplifier sitting out in the weather right on the side of the feed horn. Electrically, that's the most logical thing to do. But from a thermal point of view of the receiver, it was no good to have that LNA out there. So we're proposing to put the LNA inside the large cabinet. I'll just quickly whiz up to the top again. I don't show that there, sorry. It's in this document here. So that's the large external cabinet that we have the receiver and the status monitor and what have you. So I'm proposing to now put the low noise amplifier inside that cabinet where we can manage the temperature, manage the weather condition of that device. I've also started looking at even more significant changes to introduce a noise source. We did actually purchase a noise source when we got that receiver from Radio Astronomy Supplies. This is the item here. It says that it's got a reference output of 166,000 Kelvin. So the proposed new configuration is to have a RF switch where we can switch between the LNA and this external noise source. We're going to also propose to cool down the LNA with its own individual Peltier cell, and we'll try to thermally stabilize that to something around about 4 degrees centigrade. That's experimental at this stage, so a bit of testing will be required. And the idea of switching the noise source in is that we don't have to worry quite as much as we currently have with this drifting of the front end. The drifting of the LNA and the front end combined is a significant change in the receiver sensitivity. But when you can go to a noise source, it's not so critical. And this was a recommendation by the parks astronomers as well. I have done some testing on this noise source. It seems to be pretty stable. The actual componentry on the circuit board, it's a Schottky diode in reverse bias. I've chilled that up with instant freeze, taken it down to about minus 30 degrees. I've cooked it up with a hot air dryer, took it up to about plus 40. And that noise source seemed to be delivering the same level of output. So that's going to be quite a stable reference. At least that or something like that seems to be essential for what we need to do. And it is a practice that parks do as well. So,
quick question on that
okay.
page. Quick question. Go back to that. What's the length of that coax cable where you propose to move the LNA to the feed horn back to the box? What length and what type of cable would be interspersed between that LNA and the feed horn?
That's a very good question, Alex, and I'm well aware of the fact that we're going to introduce a loss. It's LF400, I believe, LF400.
Is it inches? Is it inches or feet?
It's going to be probably about 1 foot.
Okay.
It's going to introduce possibly 0.3, 0.4 dB loss. It is LF400, very low loss cable. At the moment, we had the LNA and then a meter of that cable before it got to the front end. So we're also going to see a loss, Alex, with the introduction of this switch. The switch was never there. that's going to introduce about 0.3 dB loss. So we could be talking about half to maybe 0.6 dB loss before that LNA. I accept that. That's a reality. I'll stop there because there's quite a lot of complex details to present. But I'm currently in the process of completely repackaging our receiver. There's the LNA. I've taken that down. That was never meant to be a waterproof unit, but I'm about to turn it into a waterproof unit. I'm going to turn in the receiver into a waterproof unit because that was in a 19-inch rack box. That was never meant to be up on the tower in a waterproof scenario. I'm repackaging that receiver board in a shielded box that will be waterproof. There's a lot of changes coming to really smarten up this receiver and getting it stable, but getting it reliable as well.
A quick comment here is that Jeff Lickman, who owns Radio Astronomy Supply, was the founder of SARA, and
Okay.
he just retired. And so the other thing is that is that a Spectre Cyber 1 or 2, by the chance?
Oh, that's a
receiver.
good question.
But I've got
I'll
just
just
to let you
check
know,
on that.
I've got a Spectre Cyber 1 sitting right 2 inches from me.
Yep.
And I've got a 3-meter dish with an LNA, 2 LNAs, 60 dB out in the open. And I've got tons of gain. So I don't think with your dish, you're going to have an issue with hydrogen. I think what you've got is plenty, even with that 1 LNA. And at a minimum, if you get problems with the LNA, add another one. Just to, mine, I have 100, well, not 100 meters, but about 130 meters of cable from the LNA to my ham shack where I've got the Spectre Cyber 1. And
Yeah, the second
that's why
part doesn't matter. That can be some distance away, can't it?
Right. Right.
Yeah.
So, but I have all sorts of gain with a 3-meter dish and that initial LNA. So, I don't see an issue. And by the way, the TED software, he originally started with my output from the Spectre Cyber 1. So the format, Ted, I think you can handle their format because it's a Spectre Cyber format, just like I have.
I have processed yours, which is Spectre Cyber 1, and I think I've processed Jay's, which is Spectre Cyber 2. There's not much difference in the format, and I think we can do even better than that as well.
Yeah. So,
Well, Rich, this is the data, the manual that we were supplied with our receiver from RAS, and it's described as Spectre Cyber 1.
Right. So you got the exact same thing I've got on my desk next to me with the same software probably. And so Ted can, by the way, Ted can actually process your data, and we could send our data to you, and you can process our data from the Northern Hemisphere.
Okay. Look, we've got 2 lines of attack from our perspective. This receiver delivers A voltage, which we've done some work with, by the way. And in fact, I've actually been published in our club newsletter, which is for the ASV, is called Crux. And 12 months ago, I did a survey just in the area of our Southern Cross, which is also Crux. And I just did 56 points, I think it was, across a grid, got the voltage in continuum mode and did a graph and a chart. And that was also then processed in a continuous spectral display. So that was quite a nice little first off run of using our telescope a year ago when everything still worked. And at that stage, I went back and double checked a lot of the earlier measurements I took, because it took about 2 hours to do this grid of samples as the dish is moving backwards and forwards. And I thought, well, I better double check some of those earlier measurements when I got to the end. And I went back. This was done in March, and the temperature was actually nice and stable in the morning. So everything was on my side, and I got what I believe was a stable measurement. But that hasn't always been the case. We've done a recent one earlier this year, didn't we, Phil, in the hot day of summer? And the temperature through the day was just skyrocketing up. So the work we started off in the morning, it was completely drifted away by the afternoon. You went back and double checked your previous results. It was completely useless. So there was nothing stable about later measurements we've done. That's always been a problem to me. And we're looking at ways of avoiding that kind of scenario. So what was I saying? So the receiver delivers A voltage. That's still useful to us. We're still going to go down that path of getting that side of the receiver to work and become stable. But we're also going to split off and go into software-defined radios at the 70 megahertz output. And we've got a clever guy who's joined our group. He's a PhD. In fact, he's a professor, ex-CSIRO. He's really keen to get involved. He's written his own code for this kind of thing already. And we're going to look at doing things at the SDR end of things as well. So I hope we can converge in our ideas here, Rich. You might give us some ideas, but we might be going in another direction as well.
Oh, we'll take your ideas too. We're not.
Okay.
And by the way, I have all sorts of problem with temperature too. So I've not solved the temperature problem. But I think Ted, do you want to show them some of your? We got a bunch of, Ted just put up a bunch of YouTube videos on his software, which I think compensates for some of this temperature issue. And Ted?
I hope so. Yeah, I don't mean to push this too hard, but I offer a solution which touches many of the things you're trying to fight. Rich is very kind as a cheerleader here. He calls me a guru, and I'm afraid of that term. I might know a little bit about it, but I'm still learning this Python, and there's lots of evidence up on the web to show that. So don't get too excited here, and please challenge me. Rich also says it controls any kind of SDR, and that's really not true. My software, I know already doesn't control, what was it, an E1400 or something like E14000 or something like that receiver. Apparently my software only knows how to talk to RTL front ends or back ends of these SDRs. And so that's the $12 kind of receiver, maybe $35 if you get the right temperature stabilization stuff, which is my sweet spot. I'm trying to go for entry point and really cheap stuff. So that's fine. There are lots and lots of collectors. So as Rich pointed out, we got a SARA YouTube video collection, and it's growing tremendously. And I'm throwing some of this Ezra stuff in there. I've almost got 2 hours up there already, so if you can stand it. And I got lots more planned, and so you can decide how much you can take. Please challenge me and improve the product. So this is fine with me. Let me go through some of the slides I have, if I can share and get this thing going right. I put all the pictures up in here. Let's see, now I got to push this button. And then I got to find the right thing. I think it's this one. Yeah, okay. So here's Ezra, Easy Radio Astronomy, EZRA. And let's see. Here's one picture that might be helpful that's in the video. We talk about the antenna being up here. There's some kind of radio. So those are the two hardware things. And then we go straight into all kinds of software. My software came up with a program called Easy Collect or Easy Call, but also there are lots of other choices in here. Alex is having a great time with SDR Sharp and an IF average plugin in there. I learned on an MIT Haystack SRT program. But here's SpectraCyber being circled. I hope you see my cursor bouncing around. And it creates a data file of a certain kind. And I have a way to get that into a common minimal data format shown down here in the bottom right. Excuse me. And so we can accept a whole bunch of different kinds of software data files only because this data format is so minimal. I can go through all that detail, but so does the video. What you were talking about was how we could either collect from a SpectraCyber, as shown here through a data file, and that's good. But you're also talking out of the radio that you're actually putting out some intermediate frequency. Maybe it's 70 megahertz, you said. And I'm
70 megahertz, yes, Ted, 70.
And so I'm thinking that you could put an SDR right into, well, I guess it would be here, 70 megahertz out of whatever your system for an antenna is. And
oh, no, 70 megahertz out of the front end of our RAS receiver. So before it goes to the back end, which does all the DC processing and square law detection, we've got the 6 megahertz raw output of the receiver front end at 70 megahertz.
Yes. So Dopplering around some center frequency way up at 70 megahertz. And that's
Yeah.
where I'm thinking that you could put this, $12 radio or $30 radio and just receive it at 70 megahertz.
Yes.
Where all my numbers say 1420, you just say 70. And,
Yep.
It'll work out just fine. It's as long as it's moving around the center frequency. And then you process it with at least Easy Call will know how to get there. So that would be one quick way to just tap into your electronics into a circuit with one radio addition, that little, dongle of a radio, and get right into all this capability. So either you could go through Spectre Cyber or you could go through Easy Call, or even SDR Sharp, I suppose, too. I think those two would have an advantage that they would have a larger data bandwidth than the Spectre Cyber, which I think is less than 4.2 megahertz. It seemed rather narrow when I was playing with Rich's data. It just doesn't have as much frequency spread to play with. And that becomes important here later. You were worrying about temperature stability. Let's see if I can pull up. Yeah. Yes.
By the way, our discussions with.
So I'm going to try to get
Ted.
through a whole bunch of pictures here to the last one. I think it's going to.
Oh my goodness! Look at that. Yeah.
Yeah, this is the video stuff, and it goes on forever now. Let's get to that in a moment. But I'm trying to get to the one that's numbered on the very end. And this is the only way I know how to get there. You're just getting noise until then.
By the way, Ted, you mentioned bandwidth.
There we go.
The bandwidth issue. The Parks people mentioned in our meeting with them the other day about having a receiver with a bandwidth of 60 megahertz.
Yes, we can all dream.
We don't have one
that's
of them.
right.
We don't have
and that's
one of
actually
those.
what Rich is doing as well with his big 60-foot dish to get pulsars. You want a great big bandwidth, but we can live with 2.4 megahertz is terrific. But I don't think the Spectre Cyber even gets to that part.
Oh yeah, it does. It's 6 at 3 dB down. It's 6 megahertz.
I didn't see it in the data file, so I'm confused.
I've measured our receiver. It's in the spec to be actually 8. They say in the spec that it's 8, but I've measured the 3 dB point to be 6.
Well, you have the advantage of reading the book. I just started pushing buttons. So
Okay.
we can work on that. There are opportunities there. I found that the SDR dongle will provide data faster than the Spectre Cyber. And I don't know about the quality. So there are other issues we can discuss. Now, but let's get to the temperature stability before we run out of too much time. This is a picture of Pablo's dish down in Los Angeles, California. Does my cursor show up? Do you see here in the nighttime that the temperature is stable and cold? So the amplifier works better and has higher gain, therefore a higher signal. But suddenly at a certain time of day, the sun comes out and really warms up the air. And so we see gain changing because of temperature. My software can handle this by comparing the frequencies that have hydrogen to the frequencies that don't have hydrogen. The ones that don't have hydrogen are affected by this gain just as much. And we can use that as an indicator of a recent measurement of gain in the system. Now, if you'll live with me, I'll show you a picture of all that. But of course, it's at the beginning of the alphabet, so it's way back here. Pardon me as I blink through things that are in the video.
So is this an attempt to correct for the temperature variation rather than trying to attack the sensitivity problem of the receiver?
Correct. I'm doing it
Okay.
in cheap software, free software,
Okay.
instead of money and hardware.
Yeah.
This is the picture that describes some of that. Can you see very faintly that there's a sinusoidal curve where my cursor is going?
Yep.
It depends on your video and how good you zoom is, but there's something in there in the hydrogen frequencies near the zero Doppler, which represents 1420 megahertz frequency going up on the right, on the left here. So this is where the hydrogen is. And up here in this box, there's no hydrogen. Same thing down here. So yet we see these stripes, curtains, I call them, all the way up and down on certain samples as the temperature changes. I have the same temperature problem with this dish here in Colorado as Pablo does. It changes during the day, a cloud comes over or a wind blows, something like that. The temperature changes and I get this variation, but it's across all frequencies. So let's use this information up here to compensate. And with that, then we can start doing things and removing those signals. Let's see, with just that much information, pardon me, where's my other picture? I guess this one. It smoothed out all the wrinkles up here, all those curtains. Now we need to do something about the gain to get this thing more sensitive. And we can start comparing things like, let's compare every sample, which is a vertical line here, lots of vertical lines, to the first vertical line to get rid of all that wiggly frequency dependent variation. I know it as kind of 3 humps in the data. And you start seeing the signal better just by that math. You can do more math. Here's from another signal, it looks about the same. But if you start looking at something else, like comparing an antenna sample to something else that was quite recent, like alternating references and samples, let's use a reference as 3 megahertz higher where there's no hydrogen at all. I think you could do that now and start comparing to a non-hydrogen frequency. And we start to get a picture that looks much better, like this. Well, I'm sorry, here. All by software again. So I'm comparing things. And then if we start getting rid of 1423 megahertz or some non-hydrogen frequency, whatever you pick, you could look at a more standard reference. I use a resistor. You're talking about a noise source.
Yep.
With a resistor, I can start doing the same thing and getting a rather smooth image. If I do some tricks like throw away these top frequencies and lower frequencies, the color can come out a little bit better. And then by math, of course, I can take out this middle stripe, which is often a spike on the software. And we finally get down to at least an image of what we're actually trying to see. Over 24 hours, we see a bright spot and a bright spot with a drift scan that happened to go through the galactic plane twice a day. So that's my quick introduction of maybe some of the processing. There are a couple ways to connect this into what you already have, either at the 70 megahertz position with yet another receiver, perhaps. In my case, it has to be some kind of RTL kind of receiver, but I don't think that's too painful. I think you'll get I think you'll get more samples that way than from a SpectraCyber solution as well. Or you could go through the data files already coming out of SpectraCyber.
With the RTL software-defined radio, we actually purchased and own now for our club an RSPDX. That's quite a sophisticated unit. It's not your $10 SDR. It's 400 Australian dollars. It has a 14-bit resolution. It'll go from 5 kilohertz to 2 gigahertz with 3 antenna inputs for the different spectral ranges. Very sophisticated software-defined radio. We had plans for all sorts of things with that particular receiver, but is it a bit too much over the top for this process that you're looking at, Ted?
I think my current software and its libraries to talk to hardware would not know how to talk to such a sophisticated radio.
Okay.
There might be solutions, but I don't have them in place yet.
Okay.
So you may have to come up with another dongle for an
Well, if it's only
SDR radio.
$20, that's easy to do, isn't it?
Well, that's what I'm hoping, but of course, there's always shipping delays and things like that. It could be that someone has one already.
But I guess I'm assuming too that these lower cost SDRs don't have the resolution. They don't have 14-bit, 16-bit resolution. They're much lower. Is that correct?
Money gets you something. Yeah, I
Yeah.
agree.
But you don't
I'm-
need that for radio astronomy, I've been told. It's not really essential.
I don't know about that. It depends where you're going. I'm trying to get you some fast results that then you could improve upon by replacing parts, and improving your jigsaw puzzle of parts. But you're having some difficulty putting some of the parts together, and this might be a quick way to get going and learn from that experience to improve it even better.
Okay.
Yeah, I definitely agree. Yeah, with Ted there, it's pretty easy to get one of those small RTL type units. My
Right here.
experience, I've got a one of those AirSpy. Sorry, not SDR Play. That's the one you're after there. Units got the earlier version. The libraries that come with that are a little bit hard to crack. I haven't really sort of, managed to make any improvements there myself. But there's a whole bunch of folks that are working with that. So I think eventually, Ted would be able to benefit from some of that. My experience, bits are pretty useful. The SDR Play, they're 14 bits. I guess you kind of lose a bit or two in noise anyway inside the unit. So they're not often exactly what they're claiming to be, but dynamic range is the thing that will be improved by those extra bits. And I think probably at the end of the day, you'll find the 14 bits is going to be better than the 12 or so in the RTL dongle. So yep.
In my I've got a 12-bit, Andrew. I've got a 12-bit RSP2 in this box here, and it's for amateur radio receivers. I've got separate antenna sockets, and I've also got transformer coupling between the receiver and those antenna sockets, because you don't want to join up your different antenna earths to each other. So that was something I discovered. But that's a 12-bit resolution unit, and the noise floor on that receiver is minus 143 dBm. So with 14-bit, that goes down even more. So you're dead right, Andrew. The dynamic range of resolution really makes it terrific. And it gets to the point where I think the 16-bit is almost the ultimate. If you get a 16-bit software-defined radio, you don't worry about cross-modulation or intermodulation anymore. You don't get overload problems.
I'm going to suggest that the 8-bit ADCs are maybe okay for a starter, but I mean, I wouldn't buy anything below $100. At least a 12-bit system. You get quantization noise. I mean, you have thousands of dollars and hundreds of man hours. Why have it dependent on a $20 8-bit system?
Good point, Alex.
My only problem is that my software knows how to talk to the cheap guys, not even in SDR Play, and I don't think even in AirSpy. So until you help me get a software layer in there that talks to them, this is what I offer.
Yep.
Don't be too discouraged, Ted. You've done terrific work. But what we come up with on our side with our RSPDX and the work that our guy Tim Davis is going to look at, we can share that with you. You might benefit in that way. We can do a two-way exchange there.
I'm all for it.
Okay.
Just don't know how fast you want to, or how long you want to develop versus get results.
Okay. Well, look, I think we're still weeks, if not months away from using our telescope in anger Does that explain anything? It-
I'm trying to parse that. Okay, yeah.
Okay, yeah. All right.
And then beyond this, once you get some peaks like I'm showing now, then the software, if you tell it where the scope was and what the time was and where the telescope was pointing, all the software knows how to put it up on the sky, or we can start talking about spectrums when we're crossing galactic crossings, when we're going through the plane of the galaxy. Now we can start talking about velocity and corrections and arms of the galaxy and galaxy rotation. All that's in the software already, and I have yet to explain it by video, but that's coming. So more options. There's a lot already in the documentation that's up on that website.
Excellent. Thanks so much for that.
I think that's given everyone some homework to do. Would that be right? I think
Lots to think about, Paul.
if we have a look at TED's Ezra system and look at its capabilities and then try and match it up with, Steve, what you're trying to do from this end, then I think we can probably find a meeting point in the middle.
I would just flip through the PDFs and look at the pretty pictures, you know, to get a feeling of what the thing is. You don't have to particularly read them. That's when you get the fever and can't stop yourself and want to go play.
Yes, I've started working through the videos, but my brain filled up, so I need to take some time to do it. All right.
Now, Rich, I'd like to go a little bit further with our receiver issues. And since you're familiar with the SpectraCyber, I've spent a bit of time looking at the square law detector. This is in the back end. So that takes your RF and turns it into DC. And I'll just share again the document that I've got together here for what I propose to do some corrections and upgrades to their receiver. So that I talked a lot about the front end, but then there's work to be done in the back end. And I found this device here, a logarithmic amplifier, which is an RSSI device, 100 dB dynamic range, sensitivity down to minus 80 dBm. And the level of signal that we get from the receiver front end is about minus 40 dBm. That's at 70 megahertz, minus 40 dBm. So this device would be quite capable of being a signal strength indicator of the neutral hydrogen output, receiver output. And the temperature stability of this product is extremely good. They designed them for the mobile phone industry, and the communication between a mobile phone and the base station has to be very stable, very accurate, because they're doing dynamic power adjustments, as you might know, in the telephone system to keep your battery consumption down, to keep the interference levels down. So they've got to be quite accurate, quite stable, and they've got exceptional figures, 0.009 dB per degree centigrade. I bought one of these. In fact, I bought two of them, and I tested it the other day. I squirted, got the thing down to about minus 30 degrees with liquid CO2, cooked it up with a hot air dryer. I couldn't get the output again to budge. So as an alternative to that temperature drifting square law detector, this was an option. And I pointed this out to our learned scientific professional colleagues at Parkes Radio Telescope, and they said that, well, that's a good receiver signal strength indicator, but it may not be the right thing to do because the square law detector has an incredible sensitivity, and it's much, much better for the very small signal variations you see out of neutral hydrogen. The other thing about square law is it's a mathematical function. It delivers power straight away, whereas the logarithmic amplifier, I see Andrew nodding his head, the log amplifier is not delivering a power result. So there's that trade-off, and I'm yet to experience that problem. But as I say, the square law diode in the circuit, it's not in any particular special mechanical arrangement. It's sitting on the circuit board, and it's extremely temperature sensitive. So the other option that I have, maybe, if we want to keep that true square law transfer function, is to take that circuit and put it in an oven. I don't know what you guys think about that. It seems horrible. But maybe take it up to 30 degrees centigrade and keep it within a degree or so at 30 degrees. that would stop the diode drifting all over the place, and it would still function as a square law detector.
Well, let's back up a little bit about
Okay.
the purpose, what you're trying to get as a result. There's two things. One is I've done very little continuum hydrogen work. I basically have taken the peaks of the frequency in the spectrum mode and plotted them. Ted's gone a lot farther than that, right? But your noise source is if you're going to do calibrated hydrogen continuum source, your hydrogen, your calibration thing is all you need, I think. You just have that, and if that's calibrated, then you can, no matter what the temperature is, you can calibrate it. Now, that's, I think, all you need. When your dish is going to take care of, your amplification is going to take care of your sensitivity. So you just need that calibrated thing, and then you throw that into Ted's, plots, and you've got a great source. What I have done is I'm more interested in the actual frequency of the Doppler shift of the hydrogen, because I'm measuring the rotation rate values on that. And so the calibration I use is I get a 142405 source, and I actually turn that thing on to make sure that I'm actually showing the right frequency. I'm receiving the right frequency, and I have to calibrate by frequency on those peaks in spectrum mode. All right, so there's two calibrations. You got the level calibration, and you got a frequency calibration. So, and you're going to need the level calibration along with the frequency. Now you can compare those. There's a bunch of hydrogen databases that you can compare those with. If you go to the dses.science website publications, I've got a bunch of papers in there where I've actually taken the hydrogen frequencies and figured out the rotation rate of the galaxy, where the Earth is in the orbit of the sun, how to use that for galactic navigation if you want to do that. So go to that site, because that's what you would use for the students that would get them excited about hydrogen, is the frequency plots, which you don't, as long as you calibrate it in frequency, and you just need a noise a source that's 142405, and you just sort of put it in front of your dish, and you're there, right? But try that and figure out, because other than that, if you can use that calibration source, basically you can compensate for the temperature and get a calibrated, thing. That's all you really need. So I'm not sure why you need to do all that other stuff yet. Get the calibration version done, both in level and spectrum, and then go with more sensitivity later, when you just get better as you go. All this other stuff seems too soon until you can get the basics done. That's just my point of view.
Yeah, I agree. It's a really important point about the frequency reference, and pretty easy to do. There are SDRs that transmit and receive, and they've got pretty good frequency stability if you GPS lock them. So, but yeah, I think Rich has made a really good point there about getting the students excited by. There's nothing more amazing than thinking about how fast we're all spinning, and getting that right. So pretty good. The other quick comment I would have is, it's certainly a logarithmic amplifier, good if you've got a lot of dynamic range, but then, you really need to calibrate that quite carefully for that square law. You can actually back out, useful numbers if you've got a square law detector with a log amplifier, but you need to calibrate it pretty well. I always go for linearity over anything else, make sure everything's linear. That's the key thing.
And one other thing on the collecting the data, and I think Alex, you went through a bunch of this in some of your talks, is compensating for the rotation of the Earth with the Doppler. And I forget that you found a site that actually will do that, but I'm not quite sure. I think you figured out how to do it real time in your measurements. to compensate for the Earth rotation effect on Doppler? Is that Ted or Alex?
Can I toss in a couple ideas and slides?
Yeah. Okay.
There's an online calculator. I'll find that website. For my software, I've been using MATLAB, and a French astronomer, JJ Mantois, gave me a MATLAB script, and it runs some government script in there. And so I have been calibrating my files afterwards, not real time. But I wanted to show you, rather than doing an overall brightness, there is an advantage to acquiring a spectrum with an SDR for background shift noise level normalization. And I'm going to show you this. Well, I thought, yeah. Okay, you see this? This is what, did that come up? Do you see this spectrum?
We see it.
Yeah, looks
Okay.
good.
This is what I wind up getting over 10 to 12 hours, in that this level changes. I'm still not sure why. How come I can't go on to the next slide? Oh, okay. This is what's been changing over a period of time, over so many hours. What's this? Maybe 10, 12 hours. I get this change, and this is an average level shift of what's going on. And from one day to the next, I get different shapes. I haven't checked the average temperature, nor have I measured the temperature of the LNA to see if it's in and out of sunlight. But there have been some pretty dramatic changes. And all of the data, all of the spectra is shifted by this. And so in my software, what I did, I said, okay, there is no H1 spectrum at 1420. It's all shifted from that. And so I wrote some code that goes in and finds the mean of about, I don't know, 30 or 40 channels in here. And I go through the whole data set of a couple hundred averages. I find the lowest mean, and then you have to do this in power, because noise adds or subtracts as power. Convert all the data to power and literally just subtract out that number that make everything equal to the lowest sample. And this is what I wind up getting. Unfortunately, this scale is wrong, but I just shift everything back. I removed all the drift from my data before I do further processing. And that is the LSRK correction curve. I run out to JJ Mantois' software at 1 hour points, and then I do a polyfit to that, and I use that for all of the couple hundred averages. And so this is velocity with velocity rotational error, and this is corrected, and plots look like that. That's probably not the best one I've done, but it does stabilize it. Otherwise, this thing would be really drooping down over time. So I think if you get a spectrum and you pick an area and say this shift here is only due to amplifier drift or sky visibility change, and just subtract that, take the power levels and subtract that from all your data, you'll normalize that due to thermal drift. Thoughts?
Sounds pretty good, Alex. Thank you for that.
Yes, I agree. That's what Ezra does. It compensates for the power level changing, so that's temperature variance during the day. It divides, you could subtract if you wish, some reference against it, and that takes care of the frequency response. So the different shapes of these spectrum that we get. And then Ezra calculates the VLSR for every sample afterwards and compensates. So we need that for the velocity information to be useful. Opportunities there, and the code you can steal if you wish, that if that helps you.
Right.
That sounds good. The other little thing is that when you're using an SDR, you know, I guess you're using sort of square law detectors for that analysis there, but SDRs themselves only have a certain linear range over those X bits. So you've got to take that into account as well. That will also be another factor.
That's
a bit
right.
more.
And so if we can compare that to the frequency response of some standard, I think that we can remove irregularities in the spectrum that's provided through the math of the SDR. It's important to refer to something and compare to that.
I'm aware of the time, and I think we usually go till about 11. Perhaps people can give some thought from their respective positions and then communicate via email, or we'll bring things along to the next Drake's Lounge Australia in a month's time, so we can keep the conversation going. I'd just like to show quickly the information that I got from the conference yesterday, and then I can see other people at this end, so Roger might have something to share. Rob, Rich, is that okay? Does that fit your time schedule?
Oh, absolutely. Go for it. We got at least a half hour, and so let's do it.
My computer has been playing up while that conversation's been taking place, so I'm not quite sure. My internet connection seems to be a bit dodgy. No idea why, but if something happens, that's I shall reconnect. I'm just going to share a screen, I hope, and I think if I share that one, can you see engaging students in STEM education? Yeah.
I can't see.
Right. So
You see the spaceman, yeah.
yeah. So yesterday was the PhysCon conference, the annual physics education conference, and I gave a paper on, which I've done already, on astronomy during the school day, which includes radio astronomy. So that's my Alex. That's like your system there, scope in a box. I've got replicated here. And I talked about auroras and various other things. But this group, the VSSEC, also gave a presentation at that conference, the Victorian Space Science Education Centre. And they're in Melbourne, just the other side of the city from me, about half an hour's drive. And I had a visit recently, and we've got a conversation going about what we might do. So they have programs, as you can see, for primary and secondary. VCE is our local Victorian Certificate of Education. So that's the year 11 and 12. And then they do sessions for teachers. And there's all sorts of information. So this website, just vssec.vic.edu.au, which is a pretty standard URL for education here. But in terms of programs, if I click on the programs, I'll keep this short, these are the ones that they're running at the moment. So they have a room, kids turn up, they actually kit themselves out with a spacesuit. You can see them here, complete with helmet. And they go into this room, which is set up like Mars. So it's as though you were going through the airlock into Mars itself. And they take rock samples while they're in there. And then they bring the rock samples out. And during the afternoon, they then do chemical analysis in the lab and take the results home or take the results back to school. You can see that there are quite a number of other things that they do here in STEM. That's the mission to Mars there. They do, they've got a wind tunnel, so they can do aerofoils. Kids can design their own profile and test it out. Human bioscience, quantum computing is starting to be developed, and then hands-on reach for the stars. But the one that's of interest here is the radio astronomy, which is here. This is the one that's in Talarook. There's their dish. I think it's a spider dish from memory, 3 meter. And they have a webcam. So you can, when you operate the dish, you can see the dish moving. And then they, unfortunately at this stage, it's only available for Victorian government schools. But there may be something, they're working on it, they're trying to expand to other, so the non-government schools, which is where I work. But you can see here, this is the sort of plot that they're getting, so that they can tell it to point at a certain object. And then, Steve, pretty much what you've been doing, start in the top left and click, 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 it takes the measurement. It does that over time, but it does it completely automatically and builds up this image. And then students can then analyze what are they looking at. White is bright, strongest signal here. So that's the strongest signal. And away you go. And it's all remote access. It's all done from school. So they give them access to the software, which is the generic, the proprietary software that belongs with the spider dish. And then the kids can do the analysis from their own school room, or they can go home and they can do it from home. As far as our own Astronomical Society of Victoria is concerned, it certainly sets a model for what we could offer. Phil, there may be some opportunities for conversations there about whether it's public access, I don't think so, but member access and guided analysis of particular areas of the sky using this sort of technique. But I thought it might be of interest to the group to see that. You can go and have a look at VSSEC and dig a little deeper if you've got something there of particular interest. As I say, they're not far away from where Phil is at the moment, and it would be a really good opportunity for interferometry. If we can get a data stream from the 2 dishes simultaneously, then we can certainly do something with that.
Can I make a comment about that, Paul?
Yep. Yeah, far away, Steve. Yep.
When we were up at Parkes, they were, proudly boasting their time reference standards, which was a hydrogen maser, and they had plans to buy 4 more of them. For this is to do really precise interferometry between the Parkes telescope and other telescopes around the world. They want to get 4 more of these hydrogen masers, but they're 850,000 Australian dollars each. So before we jump the gun, Paul, and talk about interferometry, time reference is the critical factor. I did tell the guys that we had a satellite-linked double oven GPS stabilized time reference in our laboratory, which gave us time stamping and a 10 megahertz oscillator reference with an error of 10 to the minus 12. And they thought, oh, that's not too bad, but they get something like 10 to the minus 20 accuracy on their references. So I'll leave it there.
Yeah, one step at a time, perhaps, Steve. We'll, Phil can get us the 850,000 at some point in the future.
Maybe we could borrow one of the old rusty ones from Parkes if they got an old rusty one in the shed.
Yeah, that's right. Once they throw away the other ones, we'll they can throw them in our direction.
Exactly right. Yeah, don't be backwards and coming forward saying, "Can we borrow one of your old ones?"
Exactly. That's right. Now, I'm aware of the very active sun, and that's been creating fantastic aurora down in Andrew's neck of the woods. So Andrew might give us a quick rundown of what's happening there. Where, as I said to the people arriving early, we've had aurora certainly in around Melbourne. So Malden, someone reported, and that's just down the road from where Phil is at the moment. and as far north as Gosford, which is way into New South Wales. So that's the aurora is going crazy at the moment. And Andrew, you've been getting a lot of interesting things, I think, from the sun.
Yeah, thanks. So just a quick update from me, which if I share the screen, it's a quick overview of what I've been doing the last little bit. So here's my backyard, if you can all see that. I'm out in the bush a bit. I'm in a little valley, which is actually radio quiet. So I'm sort of shielded from the city, but I'm in Tasmania, which is the island off the south of Australia. I'll show you a map in a second. And it's pretty dry at the moment. I'm in a eucalypt forest, and I have tree branches coming down occasionally, which destroy some of my antennas. But I've got a few different things out here. I'm very much into low cost, simple stuff. I'm kind of keen on outreach, so that's why I've been developing a few cheap things, and I build my own antennas, the bits of aluminium and bits of timber and wire and so on. But I've got a few different things here. So I've got a Yagi here, which is actually looking south, and we've been looking at some digital mode scattering off auroras. So the radio amateurs in Tasmania are interested in testing out some of the new digital modes and seeing if they can make contact with each other over thousands of kilometres. So we've been looking south when there's been some auroras. This is at 2 metres, looking at auroral scatter. So that's that little antenna. And then on top of that, a half-wave dipole, which I've been using to look at some other aspects of meteor scatter, which I'll say something about in a second. This is a 6 metre meteor antenna here I'm using to look at meteor scatter. There's a discone on top of that, which gives me some broader band. And I've got some VLF antennas here. I've got cross dipole system, or cross loop system actually here. This is a Blitzortung lightning detection station. Up in here is another type of loop antenna. It's a vertical dipole loop. And then I've got a quad dipole loop here, which gives me very good horizon to horizon sensitivity on the sun and Jupiter. It's set up so that I've got kind of maximum sensitivity along the ecliptic or near enough to it, which is quite handy. So that's out the back, and I've got a camera up the back of the place. I'm kind of into these things, multi-sensing, but trying to build, on my radio astronomy interests. So I've got a low light camera, which is useful for meteor detection and auroras. So I can use that with the radio astronomy side of things, and various other sensors, sky brightness monitor, which is good for aurora. So here's an example from my camera. One of my problems is that my southern horizon, I've got a little bit of a hill in the way, but this was just the other night during a brief auroral burst, so a bit of colour in there. So this is 21st of February. And on that night, we were doing some monitoring of some of the 2 metre digital transmissions from Victoria and Tasmania. And this is a plot from one of the SuperDARN radars. So Super Dual Auroral Radar Network. If you look that up, there are various sites in the Southern Hemisphere and Northern Hemisphere. This one's in Adelaide and is transmitting over Tasmania, and at about, I think this is at 10.9 megahertz. And the map here shows the line of sight velocity of plasma in the ionosphere, and we're seeing some quite fast plasma motions, up to about 400 or 500 meters per second. And that does some interesting things to the digital modes. You actually get Doppler shifts of a few hundred hertz in that case, so that's quite interesting. So that's my camera, and I've got this is on the All Sky Cam network, and I overlay some of my weather station and various other things on top of that, sky brightness and some sky temperature measurements. One thing I mentioned to Paul recently, I do try to, one of the problems is some good beacons for meteor detection around Australia, or particularly pretty much everywhere now that analog TV has disappeared. I use some amateur beacons, and the British Astronomical Association has actually developed their own circularly polarized beacon, and that would be quite nice to set something like that up in southern Australia. But until we get, a purpose-built beacon, I've been trying a few other ideas, which in this case here, I'm monitoring one of the aviation radars nearby. It's actually blocked by a hill from me, but I'm getting some scatter around the hill. So these radars, this is at around about 112 megahertz, and we're looking here at about 150 hertz of bandwidth here. These radars have some sideband transmissions, 30 hertz plus or minus. But we're seeing here some aircraft scatter, and at times I see these little blips here, which I've been sort of correlating with my other meteor measurements. I think some of this is probably artifacts or local noise sources, but I'm trying to see if I can make some measurements of meteors just with the vertical sky wave reflection, which might offer some advantages for other folks. And certainly the British Astronomical Association's had a look at this, and a French group as well. So nothing groundbreaking, but just kind of interesting to try some different techniques. And very quickly, just what's happening at the moment, I've got myself some SDRs monitoring some of those antennas. I've got an SDR play, which is I'm using the radio sky spectrograph software. And actually, that's a good point, talking about some of the galactic measurements. Those folks have really integrated a number of different SDRs into their software. It'd be good to actually make contact with Jim Sky at Radio Sky Software and see how he does it. You can connect a number of different SDRs to this, this system here. So I'm monitoring HF, 10 megahertz to 18 here with the solar stuff, some local interference, all sorts of radars and other sources. And I'm interested in Jupiter and the Sun and seeing a bit of activity there. I've also got a sort of a wider band system running over here, about 70 to 101 gigs up here, seeing some solar radio bursts at times. This is my meteor, one of my meteor channels down here as well. So just trying a variety of different things. I'm hoping to get some of that for the school kids to get interested in. And here's some solar stuff. I posted some stuff recently on the Radio Astronomy Facebook page. So some solar bursts here. Saw some nice drifting features in some of the solar radio emission recently. So yep, that's pretty much it for me.
Thank you, Andrew.
Andrew, what's your antenna for 70 megahertz to 1 gigahertz?
Yeah, it's a discone, but it's augmented. Yeah, I've actually got a log periodic as well, which is around the other side of the shed, which is coupled in. And one of the next things to try is some quadrature hybrids to get some circular polarization modes, because one of the problems with, well, at least at HF, with some of the solar and Jupiter bursts, is that the ionosphere, Faraday rotation of the ionosphere, has effects on linearly polarized systems. So I'll be playing a bit with that in the future.
Thank you, Andrew. Andrew's got, I'm just changing my screen. Andrew's got two things going for him. He's got a lot of knowledge in his head about this stuff, but he's also got an extremely radio quiet site. And I think you're very lucky. I guess you moved there on purpose, did you, Andrew?
Well, it was one of the selection criteria, but my wife probably didn't know a little bit about some of that. But anyway, I'm trying to keep the antennas in a certain part of my property for aesthetics. I can't go too far. Yeah, it's a great spot. We might have a visit down there one day. We'll all descend on you. Come and check it out. I'm watching the time, so. Got anything that you want to add while our American friends are with us? Roger? No, not watching, not listening.
you don't, not much from my point of view here. I'm afraid I'm in the process at the moment of rebuilding a kitchen, a bathroom, a laundry, and the toilet.
Right.
So yeah, haven't had a lot of time to do much, but it's been really interesting conversation. I've also run into the same problem as you with my internet connection, and I blame Elon again there. So I've missed a few bits here and there.
Yes.
Because my southern horizon's pretty lousy. I've also seen no auroras, which is a bit of a shame. But anyway, these things happen. It's actually really good to talk to Andrew. I sort of would like to start doing some of those more build it in the shed type of things. I do have a bit of a project at the moment. It's a little bit left field, I suppose you would call it. I've talked about it before. We have a contemporary arts festival happens near us here. And it happens every 2 years. The last one I got to talk to a guy from the Sydney School of Arts who does work with synthesizers and then controls devices with voltage controlled motors, basically. Now, at the moment, he's generating his own noise sources. I offered for him to get some noises from the stars. It's, to say it's a bit left field, bit arty, but I did mention last time I started talking about sonification, which is converting our signals into sound. It's really good that we do everything with graphs, but I've read a couple of articles lately, including one in New Scientist not that long ago, where radio astronomers were using sonification to basically to find things like glitches. It's really quite an obvious thing in a sound file to hear something change as opposed to watching it on just looking at graphs trying to find changes. So I'm interested in that. My dish at the moment is I need to put a counterweight on it. As I say, I'm running out of time, but I've got that on the bench at the moment. I did actually fire it up with an old satellite receiver, which my business used to be setting up satellite systems for television. So I've got an old analog receiver. And it worked. I did actually get some noises. I think most of them were terrestrial, but I'm pretty sure some of them came from the sky. So it was a good start. So the other thing that I need to talk to you guys about is really early stage stuff, getting things like my feed horn sorted. I remember having just a basic spreadsheet to get the dimensions for various frequencies to make feed horns. So I'm at that stage at the moment, getting the metal work for the dish organized, and then I need to start working on some feeds and some better receiver systems. So I'm hoping to get information from you guys from that. But for the moment, as I say, in the middle of a building project, I have a wife as well, and the priorities sometimes change when you've got a half-built bathroom. So anyway, I'm looking forward to talking to you all next month. So that's about all from me. Thank you.
Sounds you have plenty on, Roger, by the sound of it, and we'll get an update from you next month. Rob Lucas, I think you're the other Australian with us. Have you got anything? Is Rob there? No, perhaps not. All right, Rich, we've got about 10 minutes by the look of it. Oh no, he is.
Wait a minute. I finally figured out how to turn on my microphone. Can you hear me?
Yes, we can. No video.
Yes. I didn't turn the video on because I'm an old person, so I don't usually do that. Well, thank you very much for inviting me to the presentations today. My last exposure to radio telescope was in November. I went to Helsinki and went to the Helsinki radio telescope, and we observed the partial solar eclipse from there with their radio telescope. Okay. I'm basically an optical person, but I do know a little bit about radio. And I've been to the Jansky, I've been to the radio telescope in Tasmania, and I heard the Pulsar Vela. I have a recording of that they let me do. And I've been to Parkes and the Owens Valley and a whole bunch of other radio telescopes. Okay, but I'm not especially a radio telescope person yet, but I do have the backyard radio telescope, and I put that together and use the SDR and the low noise amplifiers and everything, and took a look at the Milky Way as it went overhead from downtown Sydney. Okay.
Very good.
Can
Sounds
I
like
say
you're-
something? Yeah, sorry, but hello, Rob. Rob and I are both in the Astronomical Society here, and I've been a little bit busy lately to get back to you, Rob. But Rob and I are also at some stage going to work on his optical observatory. I haven't forgotten you, Rob, but it's just been a little bit busy, and we do
Thank
need
you
to
very
get
much.
together with your telescope in a box. So that has things quietened down over the next couple of months. Maybe we look at a new moon weekend at Wirrina again and get together. I've actually got my dish now at a stage where I'm trying to make it portable so I can bring it down there, and we can start getting some of your feed equipment that I know works and try and put it on a bigger dish. Does that make sense?
That makes sense. But what I've been doing while you haven't been out to Wirrina, I have poured the slab for my optical telescope, cleaned all of the bits and pieces, reworking the rings, and I hope to have the optical observatory, basically up and running, in 6 or 7 weeks.
That sounds good. Well, I'll try and get to Wirrina next month. I've actually had a couple of birthday parties on the last couple of new moons, so I just haven't got there.
But no, the dome is, just about ready to be, put onto the cement slab that I had poured. I know we were going to do it by hand, but I think that was going to take months. So I just hired a truck. He came out and poured it, and it's all there now.
Sounds good. That's the easier way to do it.
Took 20 minutes
like
instead of.
Sorry, it sounds like another busy project there you've got going, Rob. Can you give us an update next month?
I'll see what I can do.
Yeah, great stuff. Rich, I'll hand back to you. We've got 10 minutes. Is there anybody at your end that would like to give a quick update?
That's a good question. Anybody in the Northern Hemisphere want to give a? I do have one thing, Roger. I refer you to Alex. Alex's a YouTube video on feeds. He's also been doing a Cantena. So those are, and I think he's got a software program that does all the calculations. So if you look at his YouTube video, he's also online if you want to hook up with him.
Roger, I just sent you a link.
Okay, yes.
I just sent you a link to a Cantena designer program that works well on the chat.
Okay, yep. Great.
Okay.
That sounds good. Thank you.
Perfect.
Could you send that to everyone, Alex?
Sure, I can do that.
Is that just for waveguides, feed horns, that sort of thing?
It's for a tuned cylindrical waveguide.
Okay.
And let's see.
It's interesting. I have seen similar formulas and so forth, and when we use them to see if it matches with the feed horn that we have for our neutral hydrogen, there's slight differences. So that's always puzzled me.
Okay, this one works. The only subtle difference is it calculates the length of the quarter wave antenna, and you just need to make it 95% of that. It's the end effect as
Okay.
typical vertical type of antennas, but that nails it well. The plus for that antenna is that if you're around cell phone noise, it has a high pass filter. It will roll off the 720 megahertz stuff coming from cell phone towers. Otherwise, that little loop antenna that I made works fine. And I have, at least on small scale, on the 1 meter dishes, the little loop antenna is, I've not exceeded that in sensitivity.
One other thing I found, Alex, with our feed horn was that we had 2 of them, in fact, that were delivered to us. And the one that we now use exclusively is better than the other one we were using. And the biggest difference between the 2, from my assessment, using a return loss measurement with a network analyzer, was the fact that the socket, the actual connector that had the element on it, was silver plated, and the other one was nickel plated. And with a silver plated connector on your monopole, you got a much better, much deeper return loss characteristic at resonance.
I've done a lot of design on antennas in 20 meters, a lot of modeling, NEC modeling. At this frequency, I don't trust any of it. I just cut and try. There are so many subtle things that can change that you almost need to start something and just make small variations. As you're saying, the coatings can make a difference.
Yep.
All right. Anybody else have any things they want to share from the SARA group? Now, I do invite all of you online, whether you're a SARA member or not, to join the listserv, the SARA listserv. I don't know, Ted, if you can put up a link to that. That's 24 hours a day. You guys can put up all your questions there, and this entire team and everybody else will weigh in and give you all sorts of ideas and feedback. They love to make recommendations. But that'll get that, I think, hopefully will bridge the time gap here between everybody. I think, Ted, if you could put the listserv link up. Now, the first time you get on, our coordinator will have to authorize you, but after that, then you should be able to get on real time. Anyway, I guess nobody else has anything.
I would add, I actually enjoy that. I joined SARA and I enjoy the listserv each day. I get the digest version, so it's quite interesting. So that's a free plug for you.
Good job. Yeah.
The other quick comment I just had, I had two very quick comments. One is I've been enjoying looking at Hamside, and I guess you guys and SARA kind of have, close relationship with those folks too. That's pretty interesting, and they're gearing up for some solar eclipse observations in the US, doing some radio stuff there. And that just kind of reminded me, or Rob actually kind of mentioned the eclipses there, and there's an eclipse it's a total solar eclipse on the 20th of April this year, which eclipses the northwest part of Australia. And I'm wondering if anybody's kind of interested in doing some radio stuff for that. It's a bit short notice, really. There are some others coming up in the next few years, but certainly monitoring some of the radio propagation.
I'm booked in on a cruise for that one, so I'll be somewhere off the coast of Western Australia. So I don't know if they're going to let me on with a 1.8 meter dish onto a cruise boat.
I'll take a little less.
Well, anyway, I'll see it.
I was able to detect the North American eclipse with the SARA solar monitor. If the transmitting station is on the other side of the eclipse than your receiving station, you should be able to, it looks like a day-night shift. So it goes up and it goes down, the eclipse actually. So I was able to detect that. You can actually see that on the, I think Ted put up the link to the publications. I actually published that in the DSES site. So if you want to set up for something like that, that's something. The Hamside group, we're deeply involved with that. Nathan is the lead on that, and I've actually co-helped one of his students put up a radio astronomy dish and monitor it. So was Ted's software and stuff. So Hamside group is absolutely join that if you get a lot of good data. They do atmospherics, and they're worried about Doppler and the how the ionosphere works and things like that. So very good group. I highly recommend that too. Okay. Well, I hope everybody enjoyed this. This is always very fun for us, and we actually have other things called Radio Telescope Observation Party and a standard Drake's Lounge, which are on the first and third Sundays of the month. You guys are all involved in that. I know there's a time shift issue with that, but you're all invited to that too. But if you join the listserv, you'll see the link to those there. But I recommend you just join SARA. You get all these notifications, and then if you want to sign up for the Western Conference, which is on the 17th of March, and you can do that online, or we're going to probably publish that and all the reports afterwards anyway. So you'll see those on your YouTube channel. Okay. Anybody else got anything?
Before we leave on YouTube, here on Zoom, we tried to share lots of information in the chat. If we open up the chat, in the very bottom right-hand corner, you see 3 dots. You click on that and you save chat. And it goes, at least on Windows, into your documents/Zoom directory. So it's not too hard to find. But there's a thought.
Yep. Well worth doing.
Yeah, definitely save your chat. Ted saves the chat, and then I put that in the YouTube video. So I'm going to add that to the YouTube video, the chat data. But here, the link there, you won't have the links. You'll have them on the video instead of the link. So yeah, go ahead and save that now so you get all these links to everything. Okay.
Just
right.
on the Western.
Well, thanks everybody.
Sorry, Rich, just on the Western Conference, remember it's a 1-day difference as well. So we're a day ahead of you on the West Coast.
Right.
So beware. Okay, it's been great. Thank you everybody for contributing and for coming along. March the 25th is the next one. So that's what we'll aim for. But yeah, the listserv, talk to one another through that. And thank you, Rich, for hosting at your end and getting everyone together.
And thank you, Paul. Good meeting you guys. We really enjoy having you guys online.
Yep.
Okay.
Thanks for all the tips. Thanks for all the tips and advice. Much appreciated.
Thank you.
That's good stuff. Thank you.